When last we left off, we were talking about law of sines, and we had just gotten into the basic triangle configurations where we use law of sines. Okay, so we talked a lot about law of sines, and we talked how we can use law of sines in the case of the situations that we talked about where we could use law of sines were in SAA, where we have a side and two angles, and where we have ASA, right? These are two situations. If we have two angles and a side, no matter what the configuration, if we have two angles and a side, we can always use law of sines, and it's unambiguous, as we're going to see in a second here, and it works great, right? Now, on the other hand, when we have SSA, and law of sines, by the way, I'm just going to write it up here. It says that sine of angle A over side A is equal to sine of angle B over side B, which is equal to sine of angle C over side C. And that works for any triangle, no matter whether it's a right triangle or not. Now, SSA is a little weird. When I have two sides in an angle, and when the angle is not between the sides, we call that the ambiguous case. And in geometry, you learned that you cannot prove congruence using SSA, right? In fact, you probably learned it the other way around. You called it ASS because that was a bad word, and that was like how you remembered to not use it, right, to prove congruence. You can't prove congruence using SSA because it turns out that that is not necessarily always going to determine a single triangle, and it really depends on the situation that you have, right? And so to understand this, let's go ahead and draw a diagram here. So let's say that I know side B, and I know side A, and I'm going to draw what I don't know in red. And so side C, all right, whatever's, and then this side just can be as long as it, I'm just going to draw it extra long, but it can be as long as it needs to be. I'm just sort of drawing the base because the angle right here is determined. So there's our angle side. We'll call this side B, and we'll call this side A. Right, and so the angle is determined, so that imagine that that angle is fixed. Like I can't, this angle right here, angle A is fixed and I can't move it. So I can make the third side as long as I need it to be, right, but I can't move the angle. So we can see in a situation like this, sometimes if side A is not long enough, right, I can't even make a triangle, right? If this angle is fixed, I can't hinge this down at all to make A connect up with the other side there. And so in some cases you have no triangle. And let's try and determine exactly how long A would have to be. So for instance, what is this distance right here? What would the minimum distance that A would have to be able to create a triangle here? Using, and of course that's going to end up creating a right triangle, right? And so this side, and so let's say there's a theoretical right angle here that doesn't actually exist because the A doesn't actually connect. But if we make that right triangle, then that length of that opposite side, you'd have sine of angle A, and then we're going to call that H, by the way. That's going to be height of the triangle H, right? And that's going to be equal to, well, sine of angle A is opposite over hypotenuse, H over B, right? So H is going to be equal to B sine A. Whoops. Right, so because little a is smaller than B sine A, we can't make a triangle. So this happens when B, sorry, not B. So this situation occurs when A is less than B sine A. Right, if that's the case, so the last angle, the angle that's across from, because in SSA configuration, one of the sides is always going to be across from the angle, right? So if the side across from the angle is less than the other side times the sine of the angle, then we know that we can't make a triangle at all. Now, in other cases, right, sometimes what if A is exactly equal to B sine A? right? What if A, in this case, so I'm actually going to go ahead and do this like I did before. Let's say, whoops. This is angle A, oops. Sorry, I just want to draw in all the labels here first, and then we'll talk about it. So let's say in this case, A is actually equal to B sine A, and it just barely touches the third side here, right? It's just long enough if it goes straight down and forms a right angle with this line right here. It just barely is long enough so you can connect it and make a triangle. Then, if that's the case, right, then we can make one, and it's a right triangle always, right? So, if the side across from the angle is exactly equal to B sine A, then we can make a single right triangle out of that situation. All right, so you can have a no triangle, one right triangle, and then the last situation is, of course, if they're bigger. So the next possible scenario, whoops, actually, let's do that in red just like I had then. The next possible scenario here, right, is if A is greater than B sine of angle A, right? Now, if that's the case, right, then I can make, what if I made the angle like that instead? Couldn't that also make a triangle? There's two ways I could make a triangle. If I have A out here, if A is longer than this length, then I can put A over here, or I can have it in right here, and that's two different triangles that I could potentially make there. So if that's the case, there are two triangles that you can possibly make with that. Now, that works up to a point. What happens, because think about what would happen if A got just as long as B. It's gonna slowly, as you're making this other triangle over here, it's eventually gonna get here. When A is equal to B, then you have an issue, right? In terms of, you can't make that second triangle if A is equal to B, right? And if A is bigger than B, then all of a sudden this point right here ends up to the left of B, and then it doesn't work any longer. So if A is greater than or equal to B, so the last situation is, and if that's the case, then the only thing you can make is that oblique triangle if A is bigger than B. Sorry, let me do this one more time. So in this case, if A is greater than or equal to B, then you can only make one triangle, and it's always going to be an oblique triangle because it has an oblique angle. In this case, you can make two triangles, and yeah, in both cases they're going to be oblique. Yeah. Okay. And the triangles that are formed, well, the triangle, this last triangle that's formed, is always going to be an oblique triangle. Okay. So we have to be careful that there's one instance where we talked about before, you can't make a triangle at all if you have SSA. And there's another instance where it makes two triangles. And there's only two separate situations where it only makes a single triangle. So when you're using SSA to solve a triangle, you have to be careful. When you have SSA and you're using law of sines, you have to be careful and realize that there could be two possible solutions, or there could be no solutions. And that depends on, once again, this whole B sine A situation here, unless A is bigger than B, in which case it doesn't matter what B sine A is at that point. So if A is bigger than B, we know we're good, right? That always works. If the side across from the angle is bigger than the other side, then that's fine. If A is less than if A is equal to B sine angle A, then we have a right triangle. But if A is greater than B sine A, then we know we might have two possible triangles, and we have to be careful to make sure that we give both possible answers. All right, so let's look at some situations here, and you're gonna use what you know about SSA talking about here. So I want you to go ahead and solve the following triangle, and I want you to figure out, right, how many possible triangles can be made, right, by looking at the relationship between the sides and the angles. First of all, figure out how many triangles are there possibly, if any, right, and then solve all of those triangles. If there's more than one, if there's only one triangle, solve it as well, which means find all the remaining sines and angles using law of sines. So the first thing I like to do is draw a picture of it, right, and draw it in the same sort of way that we drew the other one. So A is 3. So A, first of all, right away, A is the angle, is the side across from angle A. So this is the side we don't know, the side in red. Everything we know, once again, I'll draw in blue. Right? And whoops. So right away, we see that A is bigger, so A is this side, right? And this is B, and this angle has to be 40 degrees, right? And because A is bigger than B, right away we know that there can only be one triangle, right? So it's a situation where we're lucky. If A is bigger than B, then there's only one triangle. It's going to be an oblique triangle, right? So we can just go about our business as we normally would and set up our sine of angle 40, right, over 3 is going to be equal to, and this is angle B. Whoops, I'm going to do it in red though, since we didn't know it initially. All right, so that's angle B. So let's go ahead and find that. So we get sine of angle B over 2, right? And so now we got to go ahead and to solve for sine of angle B, first of all, let's get sine angle B by itself. So sine angle B is going to be equal to 2 sine 40 over 3. And then what do we have to do? How do we get the angle B by itself?
The inverse.
Yep, we got to use the inverse function. Right? We'll end up getting that angle B is equal to inverse sine of 2 sine 40 over 3. And if we plug that into our calculator, so if I plug it into my calculator and make sure it's in degree mode, I should get 25 I'll just round to one decimal place, 25.4 degrees for angle B. Right, angle C I can then find just by using the angle sum theorem, so 180 minus 25.4 minus 40 will give me 114.6. Right, so now they all have to 180. And the last side, we're going to have to get using the side C here, right? Side C, which I'm going to continue to do in red here. We need to get using law of sines again. So we'll do sine of C, which is 114.6 over little c, is going to equal sine of, let's say, 40 over 3. And I always like to use the angle that I know exactly, right? So in this case, use sine 40 over 3. Don't use sine 25.4 over 2, because this is rounded, and if you're taking sine of a rounded number, there's an error here, and you're going to get an even bigger error when you take sine of that. So use the exact values when at all possible, right? And then if we go ahead and solve for C, right? And I'm just going to skip the algebra. I think you can probably do it at this point. You can cross multiply and then divide off the coefficient. But if I solve for C, I'm going to get about 4.24. Right. So this was a case when there was only one triangle, and I knew that because A was bigger than B. If that's ever the case, then we know we're good to go and we can just proceed as usual when using law of sines. On the other hand, sometimes we don't have that. So in the following situation, if you're asked to solve the triangle, if A is equal to 6, B is equal to 8, and A is equal to 35 degrees. We're just going to go through this one step by step here. So an A is equal to, in this case, right, first of all, B is bigger than A, so we know it's when B is bigger than A, we have 3 possible scenarios. There could be 2 triangles, 1 triangle, or no triangle. So if B is ever bigger than A, we have to look at B sine 35 here, right, and figure out what that's equal to. So 8 sine of 35 is equal to, so A sine 35 is roughly equal to 4.6, right? So A is bigger than 4.6, so we know, so this is less than A, and therefore we have to have 2 triangles in this situation as we discussed before. So we need to figure out both triangles that could result from this situation right here. So for the first one, we're going to find the usual. And what's happening here? Let's draw a diagram just to see what is going on that is making this occur. Right? And the reason for this, and once again, I'll try and do the stuff that we know in blue and the stuff that we don't know in red. So the reason for this, right, is here's our 35-degree angle. This one is 8, and this one is 6, is because we could also angle this side like that, and we can make another triangle right there, right? So this would also work. So those are the 2 possible triangles that we could make in that situation. So we're going to start off and find one of the 2 triangles first, and then we'll find the other one. Now, as we're going to see in a second here, well, we'll just keep going here. Well, first of all, let's just find the first one, sorry. So what we're going to do here is we're going to go ahead and set up our law of sine. So we'll do sine of 35 over 6 is going to be equal to sine of angle B over 8, right? We'll start off just by going ahead and finding angle B, or one possible, and so that's the angle B is the angle that could have 2 possibilities, right? It could either be an acute angle like this one, or it could be an obtuse angle, right? Depending on how that ends up working out. It could be acute or obtuse, right? So we get sine of angle B is going to be equal to 8 sine 35 over 6. And so angle B is going to be equal to inverse sine of that whole situation, 8 sine 35 over 6. And that's going to be equal to approximately, and that'll be equal to approximately 49.89 degrees. Right now, that would be the acute angle. So we found this scenario, right? If it's 49.89 degrees, then it's this situation where this angle is acute, and we have side A here in this configuration. Now, in this situation, we wanted to figure out, well, if it was over here instead, what would this angle be? Right? What would this angle be if we had it in this situation instead? Well, we can figure that out knowing that this forms right here an isosceles triangle, right? And what do we know about isosceles triangles? Yeah, so going back to geometry here, these 2 angles are congruent, right? Right, meaning this angle here, right, is going to be this angle here is the what of this angle? It's the supplement. So this angle is going to be the supplement of this angle as well, right? So if this angle is 49.89 here, then this angle right here is going to be 180 minus 48.9. So this angle right here is going to be 1, whoops, going to be 180 minus 49.89, right? So we'll get 180 minus 49.89 will give us 130.11 degrees. So those are the two possibilities, right? Angle B could be equal to that, or angle B could be equal to 49.89. And obviously that's going to affect how long angle C is. Angle C is either going to be longer than both of them, or it is going to be shorter than both of the other sides, right? Side C there. Angle C is going to be determined, of course, by angle B as well, right? So I'm going to go ahead and we'll move on to the next page, and I will do the rest on the next page here. So here's the configuration we had again here, and once again, this is side C, and this is angle B, or this could be angle B, right, as well, depending. Right, so those are the two possibilities for angle B. And angle B, we decided, either equals what?
49.8.
It either equals 49 point, I believe it was 89, right? So it rounds up to 49.9, or it could be 180 minus that. So it could also equal 130.1 degrees, right? So if that's the case, if B is 49.1, then angle C is just going to be 180 minus 35 minus 49.9. And that'll be 95.1 degrees. So angle C is either obtuse or it's going to be very acute. And then that would make angle C equal to approximately 14.9 degrees, right? So it's either 95.1 or 14.9. If it's 95.1, then we'll do sine of 95.1. And if you can, try and plug that into your calculator using the full decimal precision, right, that your calculator gave you with that. So not the rounded 95.1 that I'm using right here, because that's gonna throw off your answer a little bit. So that over C will equal sine of 35 over 6, right? Or sine of 14.9 over C will equal sine of 35 over 6. Right, so one scenario is that C ends up being equal to, C either ends up being equal to 10.4, or side C ends up being equal to 2.7. So we have two separate scenarios here, and we found both of them. So when you're solving a triangle and it's SSA, and there are two possible solutions, then we have to then be careful, okay? So I'm going to give you one more example of a SSA configuration triangle that I want you to take a look at and end up solving for me. Go ahead and solve the triangle where A is equal to 2, C is equal to 1, and angle C is equal to 50 degrees. Okay? Okay, so what's going on here? We take a look at this, and the first thing we should always check is, first of all, the angle across from the side that's across from the angle, we got to make sure that, first of all, is the side across from the angle larger? And a lot of times it's helpful to actually go ahead and draw the triangle. So if I make side A, and let's say side C, right, and angle C is 50 degrees. All right, so the first thing I'm going to do here is I'm going to go ahead and I'm going to draw this diagram. Right, here is side A, side C is across from angle C, as it should be, right? These two angles, the side and angle, are across from each other. Right, so first of all, side C is smaller than side A. So we know that we have three possible scenarios in that case. Either this is long enough, right, that we have two possible triangles that we can make, right? Like if it's a situation like this where I could do it with this, or I can make a triangle like this. Or it's just long enough to make one single right triangle, or it's too short and it can't connect. So once we know that this side is smaller than this side, we have to go and figure out, well, what is 2 sine of 50, right? And if that will tell us based on the size of this compared to C will tell us how many triangles that we have. So if I do 2 sine 50, I'm going to get about 1.53, right? About 1.53, which is greater than C, right? So what that actually means is, first of all, no triangle can be made from that. And the reason for that is that C is too small. So really the way I should have drawn this sort of looks more like this. It's a situation where, right, because this angle is fixed and can't be changed, right, it's 50 degrees, there's no way I can stretch or I can angle, remember this hinge we can move, right, but even if I hinge it so it's straight down, it still is not going to connect up with this horizontal line right here. And so I have a situation where there's no triangle that can be made. So that ends up being the solution. There's no triangle. Well, there is no solution, I should say. Okay, so you got to be careful about that. Sometimes with SSA, you can't even make a triangle out of it. So let's look at a word problem now. We always know the word problems come up, especially when we're dealing with right triangles or just triangles in general. And so we have a situation here where we have the mountain and a surveyor is standing at the base of the mountain looking up at the top of the mountain, right? And then he walks 900 meters forward and looks up again. In both cases, he measures the angle of elevation up to the top of the mountain, right? And so he knows, all he knows is how tall he is. He knows that he walked 900 meters. And he knows that the first angle measured was 35 and the second was 47. So using just that information, we want to figure out what is the height of the mountain, okay? I would recommend forgetting about the 2 meters for now and figuring that and then adding that in later, and then everything else you're going to have to go ahead and use law of sines along with other things you know about triangles to go ahead and solve this. You might have to use right triangle trig at the end, but you should start off with law of sines, certainly. Okay, so the first thing I would do here in this case is I would solve this triangle right here, the sort of the sliver triangle here. And I can do that by, first of all, realizing that this angle right here, angle C, right, is going to be equal to 180 minus 47, because those are supplementary angles there. So if I do that, I will get 133 degrees for angle C. Right, and if angle C is 133 degrees, then angle A, right, is going to be 180 minus 35 minus 133. Right, which is 68, so that's going to be 12 degrees. Right, and so I have all 3 angles for that triangle. And what I really need is, if I just had either this or this side, if I had any of the 3 sides of this right triangle, I could find side B here. And then if I just add 2 to side B, I'll have the height of the mountain. So if I can find this side of this triangle, that gives me one of the 3 sides of the right triangle here, and I can finish solving for B. So I'm going to go ahead and use law of sines to solve for side I guess side B here, right? So if I go ahead and solve side B, so I will do sine of angle A, which is 12.5 degrees, sorry, which is just 12 degrees, I don't know why I said that, over 900 has to equal sine of 35 over side, oh, I guess, well, that's not really side, I won't call it B, right? I'll call this, I don't know what I'll call it. I'll call it side D, I guess. So call that side D. So sine of 35 over D, and I'll get that D is roughly equal to, D is roughly equal to 2,482.9 meters. Right, and so now I can use that along with right triangle trig to find B. So I'll end up getting that B has to equal, well, sine of 47 is going to equal B over D, right? Sine of 47 here equals B over D, opposite over hypotenuse. So D will just equal, sorry, B will just equal D sine 47, right? So in other words, 24 82.9, right? 2482.9 times sine of 47, which is going to be approximately, that'll be approximately 1,815.9 meters. And so the mountain itself, h, is going to end up equaling that plus 2, so 1,817.9 meters once I add the additional 2 feet, right, for the height of the guy here. And that's the height of our mountain, right? 1,817.9 meters tall, right? So someone said, well, is that going to be the height of any mountain around here? Well, let's check that out. So 1,817.9, roughly, there's about 3 feet per meter. There's actually a little bit more than 3 feet per meter, but it's roughly 3. So if we do that, then that's 5,453. So this mountain would be even taller than Mount Katahdin, which is roughly a mile. How mile is 5,280 feet, right? So this is taller than Mount Katahdin, right? But not quite as tall as Mount Washington. So this could be like a mountain in the Presidential Range in the White Mountains, potentially. All right. The 2 triangle configurations that we haven't talked about yet, because we can't really use law of sines to solve them, are SAS, side angle side, right? And so that means that we have 2 sides and the angle between the 2 sides, right? So it could be, here's my triangle, I know this side, and I know this side, and I know the angle between the 2 sides, right? And that's an SAS triangle right there, right? And the red stuff I don't know, right? So I can't solve an SAS triangle using just law of sines because I don't have any side across from any angle, and I can't find these other 2 angles, right? If I had this angle or this angle, I'd be good. But I need a side across from an angle that I know to be able to use law of sines. So I can't use law of sines for SAS. I also can't use it for SSS, which is also not that tricky to conceptualize because I don't have any angles, right? I need angles to use law of sines. I have to have them. If I don't have any angles, if I only have sides, law of sines, we're out of luck, right? So SAS and SSS can't use law of sines with, and that's where law of cosines comes into play. These are the triangles that I need law of cosines for. And so in keeping with sort of the way we've been doing things, we're going to skip the proof. There is a proof in the book if you want to go ahead and read it, and I'd recommend reading it, especially the proof for also the proof of law of sines. Make sure you know proof for law of sines and law of cosines, and you're not going to be tested on it, but it's just a good thing to know where it comes from. But we don't have time in class because of the speed we were trying to go at to do that, so we're just going to go right into it. And so law of cosines says that, and I'm going to go ahead and label all these sides. Let's say this is A, let's say this is B, let's say this is C, right? And then we have angles A, B, and C across from those. Then C squared is equal to A squared plus B squared minus 2AB sine of angle C, right? That is one of the 3 cosine, because it's law of cosines. Cosine, of angle C, right? And that's the one that we would want to use, in fact, to solve this situation right here. But it's also true that B squared is equal to A squared plus C squared minus 2AC cosine of angle B, and A squared is equal to B squared plus C squared minus 2BC cosine of angle A. And I actually don't, this seems like sort of a tough formula to memorize, especially since there's 3 of them, but I don't actually find that this is a difficult one to memorize because remember that this side is always across from this angle. So if we have side C on the left side, then we have angle C over here, and then the other 2 sides are incorporated with this situation here where we have you know, the sum of the squares of the two sides minus 2 times the product of the two sides, right? So whatever the other two sides are end up in here, and then this angle is always crossed from this side, no matter in every configuration there. So I actually, once you get that sort of pattern down, I don't think memorizing the law of cosines is too difficult. In any case, you will have to have it memorized. Unlike in Algebra 2 on the final exam here, you will not have any formulas. So you need to know law of cosines off the top of your head, just like you need to know law of sines. So please have those memorized. All right, so there's the formula, and the great thing about law of cosines and SAS and SSS is these are completely determinate forms of triangles, meaning there's no ambiguity with SAS and SSS. We could use those to prove congruence right back in geometry, which means that if you have side angle side, there's only one possible triangle that can result from that. Same thing with SSS, right? So we don't have, there's only a single triangle that can be made in either case. So law of cosines is a little bit more algebraically difficult because we have more complicated formulas, but conceptually it's less difficult because there's no guesswork. It's just, or there's no wondering whether, you know, you can even make a triangle with this. It always works. You just got to plug the numbers in correctly. So let's look at an example. Let's solve the following triangle. Right, solve the triangle if A is equal to 2, B is equal to 3, and C is equal to 60 degrees. Right. So I'll go ahead and draw the diagram, and then I'm going to have you go ahead and plug into the formula and see how you do on it. But let's just, it's always good to draw a picture of your triangle. So we have two sides, right? Maybe this is side A and this is side B, and we have the angle between them, which is 60 degrees. We don't know the third side, right? And we don't know the other two angles, right? So this is a situation, we can't use law of sines because we don't have an angle across from a side, so we have to use law of cosines. So plug all that into the formula and solve for what you're trying to find, which is to say solve for whatever you need to first and then find the rest of the information. And once you think about this, is once you've used law of cosines once, you might at that point have enough information to use law of sines. So a lot of times you'll use law of cosines and law of sines in concert with each other. All right, so give this a shot. Using law of cosines here, we'll end up getting that c squared is equal to 2 squared, whoops, let's erase all that. 2 squared plus 3 squared minus 2 times 3 cosine of 60, right? If we plug everything into the correct places. And so we end up getting that c squared is equal to all of that. C ends up being equal to c squared is exactly 7, so c is going to be exactly square root of 7. Okay, and so now that we have C, we know the length of a side that's across from an angle, and we can go ahead and use law of cosines. So we can do, of law of sines. So we can do sine of 60 over square root of 7 is equal to, let's say, sine of angle A, which is this angle right here, right? So sine of angle A over 2, right? And so we'll end up getting that sine angle A is going to be equal to 2 sine 60 over square root of 7. And sine 60 actually is square root of 3 over 2, right? From what we remember about our special angles. And so we'll end up getting square root of 3 over square root of 7, which will rationalize to square root of 21 over 7. So that's what sine of angle A is equal to. So angle A is going to be the inverse sine of that. So inverse sine of square root of 21 over 7 is going to be 40.9 degrees. Right, and then lastly, angle C we can find by using the angle sum theorem for the triangle. So subtract 40.9, then subtract 60, and we'll get 79.1. So we have found angle C, angle A, and side C. So we found all the 3 missing pieces of information using law of cosines there. Okay. Now, it is a little bit trickier. So this was a situation where we had side angle. I will say, when you have the other situation, right, side, it actually ends up being a little bit trickier algebraically. A is equal to 4, B is equal to 3, and let's say C is equal to 6 in this case. Right, when you're using law of sines in a situation like this, when you have side, be careful to first keep track of what side is across from what angle. I'd recommend the first thing you do is draw a diagram of the triangle and label all your sides and angles, then plug into law of cosines, and then as you're solving for the angle, you're going to end up having to use an inverse cosine function. Make sure you keep everything exact all the way up until the point you take inverse cosine. Do not use decimal approximations in your calculations when at all possible, and if you have to, make sure that they're out to the full decimal precision of the calculator by storing it into a memory location or something like that. Okay, so be careful when solving law of cosines for the angle that you're looking for in this case. So give this a shot. So, in this instance right here, we have a side situation. We have one side is 6, one is 4, and one is 3. So why don't we call these, and side 6 is across from vertices C, side 3 is across from vertice B, and this is A. So we have it labeled. Make sure you know which is A, which is B, and which is C. So we go ahead and plug it in, and let's just go ahead and solve for angle C first. There's no other reason than that. So you can pick any one of the three, and I'm just going to go for C. So C, which is 6 squared, is going to be equal to 4 squared plus 3 squared minus 2 times 4 times 3. Cosine of angle C. Right, so that's how that should set up. So the first thing we should do is solve for cosine of angle C, and we should do so in a way that we get an exact figure, right? And it's all addition and subtraction and multiplication. There's no division going on here. So we can keep this exact, right? So we'll end up getting 6 squared. I'm going to start off by dividing off the 4 squared and the 3 squared. So 6 squared minus 4 squared minus 3 squared is going to be a negative number, right? It's going to be positive. It's going to be 11. Oops. And then 2 times 4 times 3 is 24. So we'll end up getting that cosine of angle C is equal to negative 11 over 24, right? That's exact. So angle C is just going to be equal to inverse cosine of negative 11 over 24, right? If we plug it into our calculator, we will get 117 point, I'm going to round to one decimal place, 3 degrees. So C is 117.3 degrees. All right, so now we have angle C and we have side 6, and so we have situation where we can go ahead and use law of sines for the next one, right? Now, one thing to keep in mind is when we're using law of sines, even if we have a determinate triangle like a side, law of sines is going to think here, if this is 117.3, right, and this is angle 3 and angle, let's say we want to find angle B, angle B first. So we have angle B, side 3, and then angle C and side B. So what we have here is we have side, angle, right? So it thinks we have side, angle, right? So we got to be careful here to make sure that there's only one triangle, and we want to pick it. We want to pick sides that are going to make that happen. So this is the side across from the angle in this side angle situation, and this side is longer than this side, and so there's only one possible triangle that we can end up with in this situation. So make sure that you don't have an ambiguous case where there's 2 possible triangles you could get. Like, let's say I had solved for angle A first, right? So I knew angle A. And let's say, and so angle A is across from side 4, and let's say maybe I wanted to find angle C, right? Because 4 is less than 6, right? The side across from the angle, right, is less than the other side in this side angle configuration. I'm going to have a 2 triangle situation right here when I'm solving for angle C, and I got to make sure that I get the angle that I want and not the other angle in that ambiguous situation, because there's only one possible angle that angle C could give us. But the side-side angle situation, when the opposite side is shorter than the closer side, the adjacent side, there's a possibility we'll get the wrong answer. So in my situation, I know side C, and I know the side across from that, so and the side across from the angle, right, the opposite side in this case is longer than the adjacent side, so there's only one possible triangle that can give me. So I'm safe, but I have to be careful when I'm using law of sines in these side situations. So I'll do sine of 117.3 over 6, and then I'll go for angle B first, I guess, equals sine of angle B over 3. So if I solve for sine of angle B first, that's 3 sine 117.3 over 6. And when you're doing this, don't use 117.3 here, right? Use the full decimal precision of this in your calculator. So either do second A and S from when this got spit out, or save 117.2796127, whatever it is, in a memory location in your calculator so that you're not getting an inaccurate answer. In any case, what you should get roughly is 0.444, and so angle B is going to be, and that's approximate. Once again, this is also approximate, so you got 0.444, which is approximate, so don't use 0.44 when you're taking inverse sine. Use the full decimal precision in your calculator, and if you do that, you should get 26.4 degrees for angle B, right? And then angle C, sorry, we found angle C now. Right, we have angle B and defined angle A. We don't need to use law of sines or law of cosines. We can just go ahead and subtract from 180. If we do that, we should get 36.3 degrees. Okay, so there we go. We found all three of the angles in that side triangle. We used law of cosines, then law of sines, and then finished up with 36.3. Another way you could have done this, which might make it easier for you, if you're not comfortable dealing with this law of sines and with the ambiguous situation possibility, what you can do is instead of for the second iteration using law of sines, you could just go ahead and use law of cosines for a second time. So if I wanted to solve for angle B using law of cosines, I'll just plug in everything for B, 3 squared is equal to 4 squared plus 6 squared minus 2 times 4 times 6 times cosine of angle B. Then you have to go through all this process again to solve for angle B. So you can either use law of cosines twice, or you can use law of cosines, then law of sines. But the final angle you should always solve just by using the angle sum theorem, because that's just as accurate and a lot faster. All right, so that's law of cosines. That's pretty much all you need to know about law of cosines. We use it in two situations when we can't use law of sines. That's side, and side, angle, side. Other than that, we don't often use it that much. Formulas, right? We wanted to list the last topic. We're going to go a little bit over today. So if you guys need to take off, you certainly can. But area of a triangle. Right, area of a triangle. If I have a situation, and once again, all the derivations for this are in the book. Well, this first one of the areas is easy. So if we have SAS, let's say. So here's a triangle, and I'm going to put in blue all. Let's say I know two of the sides, and I know the angle between the two sides here. Right, so this is, let's say, triangle. This is C. This is A, and this is B, right? And so this is side B, this is side A, and this is side little c. And this forms, if I draw an altitude of that triangle, that's going to give me h. Right? We know that the area of this triangle is equal to 1/2 base times height, right? In this case, it's going to be 1/2. The base, in this case, would be c, and the height would be h. So 1/2 base times height. Right? Now, using right triangle trig, I know that h, right, let's say, and it doesn't matter which one, let's use this triangle right here. H, right, sine of A is equal to h over B, right? So h is going to be equal to B sine A. Right? And so there we go. Even if I don't know, I don't have to solve for h directly. I can just use 1/2 CB sine A, right? And that'll give me the area, which often, for whatever reason, they may have K be the area. I like to continue to have it be A. So if I have side C and side B, and I know angle A, right? So if I actually used the wrong one here. So let's assume that I know, so instead of knowing B and A and having angle C, let's say I know angle A, so I sort of screwed up this diagram. I'm just going to draw it all in blue so it's not confusing anymore. Right? So let's say I know angle A, side B, and side C. I just plug it into this formula, right? And that would give me, right, side, angle, side, right? If I have side, angle, side, right, then I can use this formula. And through the same derivation, I would find that A can also be found from 1/2 AB sine of angle C, right? So let's say that I knew BA and the angle between, SAS, right? Then I could use this formula. And the same derivation would give me 1/2 AC sine of angle B. So in any of the three possible SAS configurations, side angle side, or side angle side, or side angle side, I can use one of these three formulas here, right, to find the area of the triangle just by plugging into the formula. And it's derived very easily from right triangle trig by just drawing in your height and then using trigonometry to find h and then plugging it in, okay? So we can use any one of these three formulas, right, if we have side angle side. Right? So, but we need side angle side. And so if we don't have it, and we want to use these formulas, then we have to go ahead and either use law of sines or law of cosines to find the missing pieces of information that would get us to having SAS. Because if we don't have SAS, we can't immediately use law of sines. We're going to have to find some more information first. Now, on the other hand, if I have SSS and I don't want to have to, and this is going to involve a lengthy derivation that we're going to skip, but let's say I have no angles and I just know the sides. I have sorry, my drawing is getting really bad here. Close enough. So let's say we don't have any of the sides, we just have SSS. Right? If that's the case, we have another formula we can use called Heron's formula, which is derived from law of cosines, because law of cosines can be used in an SSS situation, right? And you can actually see the derivation. It's actually not a really crazy derivation, and it's in your book. Once again, we're gonna skip the derivation of this one. But if I have SSS, I can use the formula. I don't know. They call, for whatever reason, your book calls A the area K for some reason, but I like to call it big A. Although that does get okay, so we'll call it K from now on, because I don't want that to get confused with angle A. So Heron's formula says the area is equal to the square root of S times S minus A times S minus B times S minus C. And it's kind of a pain in the butt because S, you're going to go, well, what's S? So I know what A, B, and C are. Those are just lengths of the sides. But S is 1/2, it's 1/2 the sum, the half sum of the three sides. So you've got to figure out what S is first, and then you can plug into Heron's formula to get the area. But it allows you to skip a length. I mean, that seems really like a huge pain in the butt. But if you have an SSS configuration, the only other thing you could have done is to go ahead and use law of cosines, which is also lengthy. So it's actually quicker if you have SSS just to plug into Heron's formula than it is to go ahead and have to use law of cosines to find one of the angles first, and then you could use SAS, the area formula that we derived before there. So you have two area formulas that you can use depending on the triangle configuration you end up with. And so all you have to do is know how to use them. To be quite frank, area questions are very formulaic. Find the area of the triangle. You just have to pick the correct formula or find the information necessary to be able to use one of the formulas you want to use. Because you might not have SSS. So if you don't have SSS, or SAS, then if the triangle configuration start off with and you want to find the area is not SSS or SAS, then essentially use law of sines or cosines to find to get it to that point. To get SAS in most cases, right? Because usually, if it's not in SSS to begin with, right, then use law of sines or law of cosines to get it to the point where you have SAS, and then just use the other formula. The only time I would use Heron's formula is if you have SSS, right? But I wouldn't use it in any other case. Right, so all it is plugging into those formulas essentially, or solving the triangles more thoroughly first and then using the first formula. In either case, we've already done that, and it's just a matter of plugging into the formulas. So I'm going to let you do that on the homework tonight, and then we can, if you have any questions about that, we can go over it tomorrow. So your homework is the following: page 531, 537, and 543, those numbers. So the first section here is from the law of sines section, which you already have. So this is from an old handout. Right. And these two are going to be from the new handout that I will email to everyone today. And a reminder that this is the last week of class. We will try and set a date for the final exam, which will be sometime later in August, but before school starts. We'll try and set that date by the end of the week here so everyone knows when that's going to be. All right, so have a great day.